exercise. So what was the topic of the lecture, the course units for today? Second part of control, and specifically the question how to basically pair the control values for a decentralized control system, and taking a look at basically what's necessary in order to implement a centralized control. So first of all, as you probably, hopefully, watch the course unit videos and maybe also have some experience from before, what are the major differences between the decentralized and centralized control systems? So what are possible advantages, disadvantages? Let's be specific about what's the benefit of a decentralized control system.
It would not be that complex.
That's right. But could you be a bit more specific about the complexity? So what's complex?
As to the effects of the manipulated variable on the control variable. If we are decentralized, we are just like in this example here, we are controlling the y1 through this w1 input, changing w1. And if we had a centralized control, then we would also be taking the effects of the other streams into account and controlling it through this one controller only.
Yes, that works quite well. So the simplicity is basically about the controller itself. So we're making use of single input, single output controllers. We can use standardized PID controllers, which are available either in basically the simple software form with simple tuning rules and heuristics. Everything established, works well on its own, and also as hardware components, which are pretty robust. So these can easily be implemented in a process. That's about the complexity of the controller itself. The downside is, of course, if the process is very complex, because we have to select the input and output variables which we want to use as manipulated and as control variables, and we're basically limiting ourselves with a decentralized controller to a direct relationship. In a sense, we're using the data that we retrieve from the output variable, the y1 in that case, in order to adjust our control variable, or our manipulated variable. And that brings us basically to the centralized control system. So what are the benefits here, and what's basically the downside?
Benefit would be in our real system, like our output would be affected by a lot of other input streams also, so we would be able to take into account that here.
If you don't have, let's say, a very unique correlation between the control variable and the manipulated variable, you have the nonlinearity there, so different effects, then you can install the centralized control system which takes this into account simultaneously. But what's the downside of this? So if it is in that sense more general, you can address more complex systems, more complex processes. Why not you do that all the time? Anyone else also? So although I like the discussion in a sense, but anyone else? Any idea?
It's a single point of failure.
Could you repeat that?
It's a single point of failure. If it fails, you are like the whole process cannot be controlled, manipulated if it is centralized.
Yeah. That's one of the reasons. That's completely correct. So if the centralized control system fails, there is no control system in place unless you basically say you have a central control system which works universally in the case that everything works well. This is the one that basically controls the whole system. And if there is a failure, then there is a backup system of, for instance, a decentralized control structure, which keeps the process running. So that's also oftentimes the case in practical implementations if a centralized control system is used, that there is some backup. Of course, that's more effort. Anything else about that? Generating basically the controller itself? Does it require the same, let's say, understanding of the process, and does it require the same effort as you have in setting up?
It's more complex as far as I know. It's more complex. It takes in account a lot of variables, and it's like it takes account more variables, and that means more uncertainty. It has to be based on some kind of model, right? So
exactly, it doesn't. So the first part I would disagree in that sense, because you're taking in the same input and output variables here. So
if the number of variables are same, then it's okay. But if you are like mostly centralized system, there are a lot of variables. Decentralized system takes in account like 1-2 variables mostly that I have seen.
Of course, you're tending to use a centralized control system rather than applications where you have multiple variables. But of course, the model itself is the complex part. So basically, for the decentralized control system, you usually make use of the single output, single input, single output control, standard PID concept, and basically you just need to tune the parameters of the PID model. For the centralized control system, you're usually not making use of simple correlation here, but you want to have a model which has either been fitted to operating data, and then you need to do experiments in order to get this operating data from step change experiments, or in a better case, much better case, you have some kind of more or less rigorous model of the process, for which you would first of all need to understand the process, and then of course model it with a certain kind of accuracy. We will talk about that in the second part in a bit more detail, but you need that in the first place. And of course, best case scenario, you have this because you designed the process and you have a model of that process. But oftentimes, when you look at industrial applications, there is a plant that's running. It has been built decades ago based on some universal understanding of the process, but without a detailed model of the overall process. And if you're processing some kind of raw material which has not been, or which doesn't have really the lab grade purities, then it gets more complex, definitely. And you don't necessarily have all the data, all the physical understanding of that process. So let's start with the decentralized control system. Of course, the question on one hand side, you can make use of these standard single input, single output controllers, and you can then use the established heuristics tuning rules to define the parameters. You may also use more advanced control systems which also take into account set point variations or disturbance measurements for basically the input variables. We're not talking about those in detail here. We're more focusing now on the question, if you have multiple input and multiple output system variables, so you have a multivariate system, how do you select the pairing of the manipulated and the control variables for that system? And one part of the question was the relative gain area as a systematic way for selecting these pairings. And if you look only at the process with 2 input and 2 output variables, you basically have 2 options here. Take input variable or manipulate variable 1 and pair it with output variable 1, or vice versa, pair it with output variable 2. But when the number of inputs and output variables increases, basically the possible number of pairings increases exponentially. You can make use of the simple analytic by means of the relative gain area to get an understanding of where the correlations are most favorable for your application. So what are the basic best selections for these pairings? That does not necessarily mean that if you select them accordingly, that your control system, your decentralized control system will definitely work well. But you can make the best choice. So the important part here is that in order to do so, you just take into account 2, let's say, thought experiments, limiting cases, which basically ask the question of how the process performance in terms of the output behavior is affected by the corresponding input variables, so by a manipulated variable. If you have an open loop system or if you have a perfectly controlled closed loop system. The first one is looking basically at this simplification here. So you assume you don't have any effect of feedback on your input variables. So there is basically no control. It's just the input variable going in. And if you now introduce a step change here, which you can either do by an experiment, or if you have a model, you can basically perform an evaluation of the sensitivity of the output variable with respect to the corresponding input variable, and thereby keeping the other, in this case only U2, constant. So just looking at what's the effect from the input to the output variable, you get that sensitivity, which basically is the steady state gain. So if you change something about that input, how does it affect the output variables? You can directly see what's the direct effect of the step change in that variable. And on the other side now, you take a system where you assume there is no feedback of the specific output variable that you want to manipulate with your manipulated variable, but there is some feedback from the other control variables. And if those now deviate from their set point, in a sense, there will be feedback provided to the other input variables, which they are paired with. And you now assume that this happens in an optimal way. So basically all the other control or the manipulated variables are modified in such a way that all the other control variables, other than the one that you're focusing on right now for that kind of sensitivity, are manipulated in such a way that the control variables remain constant, such that all the actions of the other manipulated variables on your target, on your control variables, so the red arrow here, give you an indirect effect of the modification of your input variable that you are looking at here in the possible pairing between the output variable and the input variable. And basically the ratio of those two sensitivities gives you then the relative gain. And this relative gain can be integrated basically as these thought experiments. So on the first hand, on the one hand side, if there's open loop control, you don't do anything about the system, you just change that input variable and see how the output variable changes, giving the direct effect that input variable on the output variable versus what happens if you have perfect control over your system for the other control variables. And basically the change in your input variable does add to that direct effect an additional indirect effect that is basically transferred from the feedback over the other manipulated variables and the effect that they have directly on the control variable that you're looking at. So best case scenario is, of course, that this relative gain is 1. So in a sense, this can happen in 2 cases. Which one would that be? Any idea?
When U2 is not affecting Y1 that much, only U1 is affecting.
Yeah, if there is no effect of the other manipulated variables on your control variable, then there will be no direct effect. So even if your manipulated variable affects all other control variables, this manipulation, or this effect of the manipulation of U1 can then be counterbalanced by modifying the other control variables. In that case, it's just U2, but assume that there are multiple control variables, multiple manipulated variables, and you might change all the other manipulated variables to keep Y2 to Yn at a constant value, and none of those control moves, so modifications of the modified variables, will have an effect on the one that you're controlling, then there is no indirect effect. The other case is if the control move that you're basically looking at, so modifying U1, doesn't affect any of the other control variables. Because if that is the case, then there is no feedback. So control loop 2 will not use any modification of the other control variable, of the other manipulated variables. So under these two conditions, either you have only a correlation between your manipulated variable and the considered control variable, or there is no effect of the other manipulated variables on your control variable. You will have a relative gain of 1. That would be the perfect case, perfect selection. By modifying U1, you have perfect control over Y1. There's only the direct effect, no indirect effect whatsoever that you need to take into account. In all other cases, there will be some indirect effect. And basically adding this indirect effect depends, of course, on the sensitivity. So if basically the output variable is increased or decreased, your relative gain can either be smaller or larger than 1, or it can also be negative. And what you're aiming for is basically finding those gains that are close to 1. If they are equal to 1, this is the optimum. If they are close to 1, this is probably the best pairing that you can select. Sometimes this might be a bit controversial in the selection. There are different options which you should check then. Oftentimes you get a good indication, but still it's in a sense a heuristic. And this heuristic is based on the information that you get from the steady state performance. So not necessarily doing a dynamic experiment in that sense. You're looking at how this modification alters the steady state performance of the process. You can do this either by means of your model or by means of an experiment. Benefits here are that the relative gain area is a dimensionless number that makes it especially valuable as an engineering tool, so it doesn't depend really on the process, on the conditions, on the scale, on the capacity of the process. You basically get similar numbers if these sensitivities act in a similar way, and thereby you can always focus basically on these threshold values and on the identification of your optimal choices. So benefit from the 2-2 system that is not directly transferred to the other systems is that usually the relative gain from 1-1 to 2-2, those are equivalent, and they, as a column sum here, they will give you 1. So basically this matrix is symmetrical and the diagonal elements are equal for the 2x2 system, not necessary for the larger ones. Okay, you had an example here that was also discussed in the video already, but we just briefly go through it. So what you're having is tag system here for which you want to control the flow rate and the composition, and you have 2 streams that are going in, and basically you can manipulate the flow rate of the ingoing streams. So basically the mixing of those streams. What you do in order to derive a simple model for that process, you just take the total mass balance and the composition that is introduced into the system based on the mixing of those streams. And based on this simple model, you can then derive the steady state gains, K11, K12, 21, and 22, where basically the feed streams, the individual ones, M1 and M2, are your manipulated variables, and your control variables are the flow rate of the process and the composition. And when you have these gains, you can further process them, get the lambda 1, so the relative gain, can calculate this for the 2x2 system directly through the steady state gains, get the value there. Basically, this is equivalent to the diagonal elements. And as you know, the sum is basically equal to 1. The codiagonal elements are 1.
Wow.
M1, 60% of the feed mixture come from M1, 40 from M2. Then you can calculate basically the relative gain for the relative gain area for that set point. It will look different for a different set point, as you see. So under that set point, what would be the control pairing that you would pursue? Anyone? Simple example. Hello. So which control variable would you use in order to control, or which manipulated variable would you be using for the control of the feed flow rate, or the final flow rate? F.
M1.
Yeah, exactly.
Closer to 1.
Exactly. Larger value close.
It's like 60-40%.
Yeah.
It's not affect that. It's not like 90-10% or something like that. So it's difficult to control it just by M1, or you can like control it just by one.
This is an indication of what are the better pairings. So it is of course a bit more different if you're at the 50% part, because the uncertainty there is closer to, if you change one of the variables, those will be affected more or less equally. If you have now affect F with M1, you're affecting the larger value, while with the small value, you're affecting the composition. If you change the set point, this will directly, so if you go from 0.6 to 0.4, it will be the opposite way around. If that makes really so much of an issue for that process, I would argue right now no. But this is the result that you get from the analysis of the relative gain area. So in a sense, you can also say that the model here is pretty simple. So it's a linear effect. There is no nonlinearity in there, and basically both are doing the same and having the same effect. But you can also say that if you modify the smaller stream, so let's say you go to the 90-10 example that you had, and you have M2 with 10%, if you change that smaller stream right now, this has a larger effect on the composition in a relative sense. So if you add 0.1 there, then you go from 10 to 20%. Okay, but let's look at a bit more complex example now with 4 manipulated 4 control variables. So assuming that you have already computed a relative gain area for a refinery process where you have the top and the bottom stream as a product, as well as 2 additional side streams. And you basically want to control the composition, some scalar value of the composition for each of the product streams by the different product stream flow rates. And you have different options here. I just picked up randomly 4, A, B, C, D. You should be able, by scanning in the QR code, to participate in this Mentimeter query, and just select one of those 4 options which you would deem the most interesting one, or most favorable one for controller pairing. First one is basically direct choice. The composition of that stream is controlled by the flow rate of that stream. So appears there's nothing more coming in, but good to see. C is absolutely right. 5 or 6 of 7 selected C. That's great. So I think the first one is pretty straightforward. So it's 0.931, the only larger value closer to 1 in the positive range. So there's a direct coupling between the composition and the flow rate of the top product. But the other three, they are a bit different. So looking at the last one, you obviously see that the composition of the bottom product appears to be well controllable with S2, which is very close to 1, as well as S1 can be used to control the composition of S2 with also almost a relative gain of 1. Only for B, there we have basically a very large value, which will potentially dampen the effect a bit of the manipulated variable on the control variable. But again, it's the only value here that is on the positive range. And even though it's not closer to 1 than B, we would now prefer this because of the other two pairings that we already had for S1 and S2. Okay, so I'm pretty sure that with that performance, you will also perform well in the exercise, where you will have a larger example where you can accelerate this in a more detailed way. So we jump forward a bit.
Professor,
Yes.
I just have a question. What does the negative value indicate? Inverse relationship or something?
In the sense of inverse sensitivity. So generally, the only thing that you take into account with the sensitivity is if it has what is basically the effect that your manipulated variable has on the output variable. So this sensitivity might be positive or negative. So if you increase your manipulated variable, it might decrease your control variable, and then you would have negative sensitivity. So if there is no effect whatsoever from the additional indirect effect there, then this will basically balance out in the ratio. So minus divided by minus will give a positive value. But if there is a now strong indirect effect, and that might go in the other direction, this may result in a different sign for the denominator of the relative gain, and then you might get a negative value.
But if we have an inverse relationship, why wouldn't we use that for controlling? Like if we know it is inverse, and if it's close to like minus 4.429 close to 1 only, wouldn't it be better to use this knowing that it's inverse?
Because the case when you have that inverse relationship, you definitely have an indirect effect.
Okay.
And the indirect effect is adverse to the direction you are basically manipulating your variable.
Okay, got it. Thank you.
But can it be used even if it's indirect? You can like model something of it.
The thing again is, if you're using this approach with the relative gain, you're doing this to implement basic single input, single output PID controllers. So basically, the model that you have in the controller is the standard PID model.
Okay.
Of course, you can move to a model-based controller, and that is exactly what we do right now. So the second part, basically, of that lecture, the second course unit was on model-based methods for control. And in order to, first of all, apply something model-based, you have to have some model there. And you have to have data, measurement data, that you can use for basically quantifying the performance and analyzing if your control move actually resulted in the predicted behavior of the system. And one possible application of models here is, of course, to use models in order to make variables available as output variables with measurements that are basically not measurable in the first place, or not well measurable. So one approach here is basically the determination of the composition of a stream. In that case, this would be the distillate product of the distillation column, where we said for standard control structure of a distillation column, you oftentimes rather refer for stabilizing control to some internal temperature measurement, and you try to keep that temperature at a set point in order to control the composition of your product. But of course, the better choice, if you have it, would be to directly control the composition of your product. You can do this either by applying some kind of measurement technique that provides you with the composition directly, and have, of course, obvious choices there. You can use some spectroscopic measurement, which, however, has to be calibrated. You have to have partially a complex piece of equipment that is also costly, but that would give you almost direct measurement of these control variables that you have there. That would, of course, be beneficial. On the other side, you can use something like a GC or HPLC measurement, which has some delay in measurement and provision of the measurement value. Again, this can be pretty accurate. Still, you have to implement a procedure there to get that, but you could use it. The only problem with that, with the delay, with the downtime there, you would have that measurement available after X minutes. And if you see that there's a deviation from a set point for the control variable, you will only act that time basically shifted in the future. Another option is that you try to determine different measurement values and use a model in order to derive the one that you're actually looking at. One option here was basically you install a densitometer and something to measure the conductivity, and you have a temperature sensor, and based on these three measurement values and models for the density and the conductivity, you can then derive the composition of that mixture by means of an inversion. So you know these two models, you know the summation condition, and you can use these models, solve this nonlinear system of equations in order to derive the compositions. These kind of measurement methods are available at lower prices. They provide you with direct measurements. Of course, the important question is then how accurate are they? So how fast do you detect some variation of the set point that is larger than your measurement uncertainty? So, but you can use this, of course, for mixtures where you can model these kind of thermophysical behavior.
But also, isn't it part of a sensor? It's a sensor, it has nothing to do with the control, right?
The sensor doesn't directly have to do with the control, but if you want, so you need to see what exactly can you control either directly or indirectly. What we said about the distillation column, we use temperature measurement and we do temperature control at some point along the stripping and the rectifying section.
But temperature may be measured by a device like RTT, may use resistance, or it may use something else like infrared or something. Will it affect that, or it has nothing to do with temperature measurement?
I didn't get the beginning.
It's like temperature can be measured like by if the method is more accurate. The simple method is by a thermometer, mercury thermometer, or something like that. But today mostly they use RTD or thermocouple or something like that, right?
Yeah.
So they depend upon different, like RTD depend upon resistor, right? Resistance. Is that a model-based system then? If I am using a resistor,
now that's the difference. So yeah. So of course the sensor itself may have some modification of what it actually measures and what it basically delivers you as a measurement.
Yeah,
yeah, and you might call this also a sensor in a sense. So if you draw a box, let's see a commentary here. If you would implement this all in a single unit, you might also call this like a sensor for the composition of that mixture, which is, however, pretty fixedly tuned here, because you need to have a model for that specific mixture for the density and for the conductivity, and it would basically measure the conductivity and the density and the temperature in order to derive these values. So this could be a sensor itself in a sense. The other part here now is basically you have three sensors, individual ones, and based on an additional model that you have there, you derive these values. But it's still only related to the measurement here. So you're basically getting information about an output variable or output variables in terms of the composition, based on measurements of other output variables.
Yeah, okay, but it has nothing to do with the control logic or control. Like it, at the end, there will be a controller. It would be a PID controller or anything like that.
Exactly. Here is no. This is not directly related to the control structure.
Yeah.
But the thing is that you either want to control something simple like the temperature, and we said if you want to control the product composition, one way to do this in the classical control concept is looking at the temperature measurement along the column height, where you know this is pretty sensitive in terms of the location from the temperature if there is a disturbance. So you can basically have a stabilizing control concept that tries to maintain the operating point by keeping that temperature at that location constant.
Yeah.
Okay. The thing you want to have is a constant composition, but you're not directly controlling that. So you have an indirect control of your temperature of your composition by keeping that temperature in the column at a more or less constant value. Right now, the question would be, can I directly control my composition, which would be favorable? And this may be done, for instance, if you have some of these sensors and can combine it with a model. So it's just about at that point, how can you make use of a model, in this term here, physical chemical models, in order to get access to your control variables in terms of the compositions. Right? That fine? Understood?
Yeah.
Okay. So that's the first part. Next thing is, of course, that you can also use models in order to get information about the internal performance of a process, or basically also the output variables. But if you use a model in that case, so knowing what the manipulated variables will do with your process to get a predicted state, we're calling about state estimation, and that is basically a prerequisite to apply a model-based control system. Because usually you cannot measure everything, and you have some state variables that are not measurable. The question is, by observing other variables related to your system, can you predict those? That gives you, on the one hand side, the possibility to monitor the process performance. So for instance, by measuring something like temperature and conductivity and density in terms of a reactor, you might be able to measure the composition in the reactor based on a model-based observer. In that sense. You're not directly measuring the composition, but based on the other properties, you may be able to estimate the composition at a certain instant in time, and thereby you can monitor the performance within the reactor online. So if you have a process model that can be simulated in real time. And of course, you have a few prerequisites that the model has to suffice to. It has to be sufficiently accurate. Model disturbances should not be neglected. Oh, there are a few typos here. Not model disturbances can be neglected in that sense. So there are no effective disturbances that make your model that uncertain. And of course, one thing, you have to know somehow what your initial states are. So if you're estimating something that is in the process, you have to have an idea of what is basically the initial state in order to perform an integration. Yes.
Sir, what does meteorologically means in this slide?
Meteorologic. Okay. Sorry, that is to be ignored, please. I have to say that this has to be something that has been done by autocorrect. And let's see, I'll get back. So, can you see the slide? Again?
Yes, sir. Yes, sir.
Sorry. So please ignore the word. Let's give me a chance to go back there. So say if I estimate value for this should generally be usually inaccessible state variables. Normally. I don't know how meteorologically it came in there. Sorry. Okay. I will correct the tables on that page. So basically, the state estimator gives you a way to get actual state information based on measurable data, measurable variables, for variables which are usually not measurable. And what we have looked at there in the course unit was the question, when is this feasible? And there was only this example of the exothermal reactor with a simple reaction A to B. It's cooled via the jacket, and we want to know what's the composition, what's the temperature in that reactor. That is what we measure, what we model. So basically, our state variables x1, x2 are the concentration and the temperature. We have differential equations for those. And what we can actually measure, other than in the example in the course unit, there was the temperature, now it's the composition. We assume basically if we measure the composition at the alpha rate, and we assume this is an ideal mixed reactor, then it's basically the same composition as we have inside of the reactor. We talked about observability analysis. So can you tell me what you actually need to do in order to judge if that process is observable and if that's the case? So the question is, if we measure only the concentration, do we have sufficient information in order to determine the composition and the temperature? Yes or no?
No, yeah, I guess. I mean, it's just a concentration, right? I mean,
yeah. So on what basis do you say no?
so I mean, to determine temperature from concentration, we should probably, yeah, maybe if it's a binary solution, then no, I guess then we need to know the corresponding pressure, because it's like
you're aiming at a thermophysical relationship right now. Yeah. But we have our state model there.
I think like degree, we will calculate the degree of freedom, like what are the number of variables that we know and also how many equations that we have. So in this case, we have 3 equations and we have only know the composition. So in this case, we have still, we need to know some initial values. So like, maybe something like that.
Let's say degree of freedom analysis is always good, but it's not the case here directly, at least not directly. Now I have to say, of course, if you have watched the video, you should know this, because it's basically explained there. The observability analysis is building on the equation for your measured variables. So y equals c, ignoring a bit now the disturbance term here. And we know if we can directly measure composition. The question now with the observability analysis is if by taking that information and taking also the derivative information of that information, can we determine the other ones? And if you do this, you see, okay, if I take the measurement C and I basically take the derivative information there, so how does Y change over time? Meaning that how does the concentration change over time, bringing us back to the state equation that we have. This gives us a link which also includes the temperature, and if we basically know what we have as a heat stream that goes into the system, what's the volume, what's the concentration of the ingoing stream, and what is the actual composition, the concentration which we actually measure, we can determine the temperature indirectly from this equation. And thereby the system is observable. Would we be using this? So would you basically track the change of concentration over time and then tell me how the temperature looks like?
I think we will have a temperature profile also, and it might change with time to time. So like it's a very variable thing. So we should not jeopardize our whole process based on this observability analysis.
That's what you would do if you, let's take the serious part and say, okay, we can implement a temperature sensor. But oftentimes, if the plant is running and you ask the question, can we judge on the temperature inside of the reactor? Then we can drill a hole in there and put a temperature sensor in there is not the answer. So then the question would be, can we take the data that we have right now and get an idea? And yes, you could basically track the concentration profile and get an idea of the temperature, knowing an initial value for that. But you wouldn't be doing that because taking the information that you measure and then basically taking the first derivative information based on the individual measurements that you have there adds up in the noise. So it basically increases the noise that you have in your concentration measurement. So you wouldn't be applying this approach, but basically just looking at the observed variables and basically at the derivative information there. It tells you if this can be done. So if you can, based on this model, this differential equation that you have there, based on that, can you get the temperature information as well, just based on the concentration information? And then the answer is yes. You wouldn't be doing this, just taking the information and taking the derivative. For a larger system, it might even be the case that you have to get the second or third derivative in order to see if there's a relationship that you can exploit. You wouldn't be doing this in application, but it's a good check to see system is observable or not. Because if it's not the case, then you definitely need more measurements in order to get the necessary information. What you actually will be doing is to implement something that is either an observer or Kalman filter that depends on the way that you basically integrate this correction term here, which gives you a correction with respect to your output variable and the estimated output variable. Yes.
Sir, if you don't mind, the concept of observability analysis is still not clear right now for me.
Okay.
Like, yeah, I'm still trying to wrap my head around this concept, but like,
this is basically the question that you pose there is, given my state model that I have of my system, basically this set of differential equations that you have here, and given my obtainable information based on measurements. So what is basically my observable information? I get as a measurement the composition. Can I basically observe both my state variables? Question clear?
question is like I have like a tab available to my concentration of the process or the composition of the concentration, and then I want to measure the temperature using that information.
Yeah, or vice versa. It's basically the same question, same answer that you have. The thing is, you have, let's say, a running star tank reactor there, and let's assume the scenario you have basically a temperature sensor and the concentration sensor there.
Okay.
Everything works well. You get basically the concentration and the temperature of your running plant. Now one of these sensors fails.
Okay.
Now you only have the information of one of those sensors anymore. Okay. Can you still, based on your model of the system that you have, tell me what is the other one?
Okay, so like this is what we have learned like about distillation column also. Like we are correlating temperature with the composition without even knowing the composition. So I think like is it the similar concept here also, because in distillation column we are only measuring the temperature, and depending upon temperature we are saying that yes, the composition is like 0.8 or 0.7, something like that. So
yeah, let's say that is a bit different depending on what you're actually aiming at. If you say you measure the temperature of your product stream,
okay, then
based on the vapor-liquid equilibrium data, there was one thing that was mentioned before as well as a physical-chemical relationship. Yep. Okay. You can estimate the composition. For a binary system that works, for a multi-component system not really, but for a binary system this would work. The other part was that if we say, let's say, draw something in here, if we have a distillation column and what we actually want to control is basically the product stream, but what we are looking at then would be a temperature here somewhere in the rectifying section. And we said, okay, this is basically, if we look at the temperature profile, this is a location which looks a bit like this from the temperature profile. Then we know there is a lot of sensitivity in the temperature profile here, and we would select this specific location with a temperature measurement because we know if something changes about the behavior of our system, then this might shift upwards or downwards, and thereby the temperature that we actually measure here will change very quickly. So we basically track that temperature in order to detect that there is a change in our system. There is no direct relationship between that temperature and the composition. We are basically building our stabilizing control system here in such a way that we say we want to keep that temperature at that instance, because we assume that if we do so, also our output variables will maintain constant. But we're not controlling directly our composition, we are controlling our temperature here.
We make our laboratory analysis first initially, and we know that at this temperature the composition was like that. So if there is going to be a shift in the temperature profile, there might be a change in the composition of my product or my feed stream, something like that. And so we are not like making a direct correlation with temperature and composition. We just know that if we change the temperature profile, the composition of product will change. So yeah, this is what we are doing in distillation column.
This is what you're doing at that point. Of course, what you would like to do is directly control the composition.
Yes. So
yeah. So however, this temperature here is something that you can easily get. Base PT100 probe there, and you get a pretty accurate temperature measurement from the gas, from the vapor phase, and you can well implement a PID control there. And for stabilizing control concept, where basically the assumption is what happens if now the heat of your utilities changes a bit, or if the feed changes a bit, not too strong, you're not operating at a completely different set point, but if you're just stabilizing the system around the set point you're actually operating at, then this works pretty well. If you want something that basically says, if we go in capacity from 100 to 80%, or if my feed composition changes by 15-20%, then this concept might not work. Or you have to adjust basically the controller to the new set point first and then activate it.
So like we are going to again use some sample points and measure the composition again in the laboratory, and then we're going to correlate like if this is the new feed, and this will be the new temperature, and this will be the new composition. We are not going to correlate composition with temperature. We will make like analysis again.
Yeah, let's say it doesn't necessarily mean that you're doing the lab scale experiments there. You might do this with
crudely, like in a very crude way, or in a very naive way. I can say that we are not correlating we are not making a mathematical model between temperature and composition. We are just estimating it. Like at this feed, at this temperature, the composition will be like that.
You might even know that in that case. The thing is, the question is what you want to do there with your control system. If this is a stabilizing control concept, it means that you're operating your plant at a potential set point, and then you're using the concept with the PID controls there to keep the system at that set point. So if there's some disturbance in the system, you're trying to basically balance this out. But you're trying to keep it at the same set point. The PID concept doesn't know about the composition actually, in this case. So it just knows that there is a set point temperature, in this instance in the column, and you want to maintain your process operating at that set point. And it will act on this, basically on deviations from that set point. It doesn't, the control system, if it's implemented as such, doesn't know about the composition of your products. That is how you designed the process, and you basically operate it at that point, and then you can implement the control structure to keep the process at these operating at this at this set point where you have designed the process in the first place to basically deliver the products at a specific quality.
And one question: can we apply this observability analysis on this distillation column just to correlate composition with temperature? It's a very layman question, but I just want to ask it.
Yeah, of course, you can build a process model. So you still need the state space model. It tells you how the states that you want to estimate, these are the products, how basically they are determined. How do they change in terms of a dynamic model? So here you have the model where you can build the balance envelope around the reactor. And this basically comes from the mass balance, and this comes from the energy balance. If you build a model for your process, for the distillation column, you can do similar stuff, of course. If you have a model for the distillation, in the best case, a differential model that tells you how these variables change, then you can do so.
Okay, so I think I somehow understand this. Thank you, sir. Thank you so much.
Okay, welcome. But let's move one step further. So that is basically just about, can we do this based on what we have as a model? And then the next step is basically building a model that actually does this. And in order to do so, you usually have to take into account something that wasted in the observability analysis. Anyway, we have this disturbance terms here, V1, V2, and WT, which somehow have to be considered. And in order to consider them, there is basically a differentiation here with a correction term that tells you how the difference between your actually measured variables and the estimated measured variables, so sensor model in that sense, which we talked about before. What sensor model tells you, what you would get as a measurement, taking into account your process model, and what your actual sensor tells you. And you're trying to basically correct your overall model in the sense that you get this deviation annihilated. Then what you get is an estimated state based on this model-based measurement method. And this is just the important factor here. If you want to use model-based control, you somehow have to consider that your model will be not perfect. So you will have a model of the system, but it will not be perfect. It will not exactly tell you how your system will react when you manipulate some of the input variables. If the direction is hopefully right because the model is structurally correct, but the exact extent to which your control actions will affect the real process will not be exactly that what you predict. And so you try to improve your model by taking into account that there are certain deviations between your measured variables and basically the proposition or the estimated measurement value that you will receive there. So that is a proposition, that is or prerequisite. That is what you need in order to apply model-based control. You need a process model. You have to have observability of your system to a certain extent, and you have to basically implement a model that also corrects for basically these deviations between the real measured data and basically the state estimates that you provide, or the output estimates that you provide in order to get accurate state estimates. And if you go to model predictive controller, this is basically what you need. In the first place, nonlinear observer model, which tells you from the actual values that you have and from some initial values that you have, what basically the current states are, and then what you do in order to control the process. And that is a huge benefit of a model-based controller. It can predict the future. Other than the decentralized control structure, which basically just tells you, now there is something not in the correct place. So now we have a set point deviation. Now I have to act, because the set point deviation is positive or negative, I have to act in that certain way in order to get my control, my stabilizing control for my system to return to the actual set point. For a model predictive controller, you can take that model, you can build on the observer, and then you can basically solve an optimization problem looking in the future, saying you, if based on my current position where I am, I do these different control actions, I will wind up in a position in the future at that point where I perfectly reach my set point without basically violating certain constraints. Constraints are a second very important point here that come into play with model predictive control. You can tell the process that some temperature may not be basically reached or breached. And you may also introduce an objective function that is not just saying, please reach that set point, reach that set point as fast as possible. There's two things you always have to basically take into account for setting up a control structure. Usually you want to have an effect of the controller that is as quick as possible, but not as rabiat as possible. So a controller may act very quickly and then potentially get into some oscillating behavior before reaching a set point, or it may act rather smoothly, but at the same time, this usually takes a longer period of time. We see that in the next part. But I somehow introduced a lot of typos here, apparently. But one big thing that you have to do here, that's pretty different from what you've seen before, you have to solve dynamic optimization problems. Yes.
So did you saying that if we make a PID controller, it would be sluggish, but the control will be better. But if we have only PE controller or PI controller, the controller will be not sluggish or maybe quick, but control might not be good. Is what you said? Is what I inferred from.
You can tune a PID controller also differently. You can use it in a way that it acts very quickly with basically a lot of force. Basically, let's say going to the upper and lower limits of the control of the manipulated variables in order to act as quickly as possible on a deviation, or you can basically have it act more smoothly. So if something happens, then basically first a lower level control action is a lower level of the manipulation of the manipulated variables coming into place to get it as smoothly as possible back to the initial set point. This is about the tuning of the control parameters. And at the same time, if you have a model predictive controller, you can also use it for quick reactions. It depends on the objective function that you specify in a sense. So what you want to do, if you want to get as quickly as possible to the set point, you can define this as an objective function, because here you're building a dynamic optimization problem out of your dynamic process model, and let this optimization model decide what are your next control actions. You can say this is either quick return to a set point or quick movement to a set point. You could also say with as few, let's say, either constraint violations if you let them take place, or if there's soft constraints, or if they are hard constraints, you can say these may not happen at all. Or you can have an economic objective function, for instance, and say this has to happen with the lowest loss of product possible, for instance.
So the trade-off between offset and the sluggishness of the controller.
That is something you have for both types of controllers.
Okay, sir. Thank you so much.
So let's say the big difference is what you can see here. The one hand side, for the model predictive control system, you're on the one hand side not only looking at this current time step. So the PID controller would just take a look, how far away from the set point am I at that instance in time, and would then perform a reaction. So would then manipulate the variables. The model predictive controller would take a look basically in the past, see how did my control moves and the predicted behavior of my output variables match to the actual output variables. That is basically what is optimized in terms of the observer. So that basically in the best case scenario, due to the correction, you will match with the estimated output variable to the real output variable that you measured. And at the same time, you will look in the future, solve an optimization problem that tells you if I do these control steps within my control horizon, then I will probably, if my model works fine, get this manipulation of my output variable. And at a certain point in my control horizon, if it doesn't change, it do not change anything around that anymore, I will wind up at this point very close to my set point. This will basically specify the time frame in which you do this, and then you can have different kind of objective functions which will result in a different behavior of these control actions. In terms of application, what you actually do is you solve such an optimization problem within that timestamp in order, in this timestamp, the one that you already passed in that sense, to determine the control action, the one that you see here. So usually you're just applying one control move, while basically you're solving the optimization problem for the control moves in this horizon. Why you're actually doing this? Because for this point in time, you know your actual output variables and how far you deviated from them, and you have quite good knowledge about what is the real behavior of the plant right now. And by doing this step, you basically predict what happens in the future, and then you perform this step in the sense of having an idea of, if I do the next steps, I will wind up at that point in my prediction horizon. But you basically resolve that problem once more in the next time step in order to determine this control action. However, at, let's say, with the knowledge that you have at that point in time. So if there's a deviation between the predicted output behavior that you have and the real output data that you gain there, potentially also you gain some output variable, if I say, before you have a composition measurement that has been performed basically at that point in time, but due to some that time that you have there in between, you get this right here. You may correct your model and thereby modify that next control move that you have. So model predictive control can take into account also data that you retrieve with a certain delay in order to correct the model that you have. So you have a lot of benefits. You can introduce an economic objective function. You can introduce certain kind of constraints on basically your manipulated variable or your predicted state variables there, so that you don't want to cross the temperature limit in a reactor or so. You get basically a prediction in the future, and you can take into account basically the data that you have received in the last steps. So not only looking at an instant in time, but you're looking basically at the past and the future. And all these benefits are obtainable with a model predictive controller, which of course you can use for centralized control. But they come at the price that you need such a model. This model has to be accurate to a certain extent. It definitely has to be structurally correct. And of course, you have to have observability based on the actual output variables that you can measure. And you have effort in generating such a model. Okay? So a lot of benefits, but of course at a certain kind of demand. And let's just look at two examples here. So again, a simple one with a two-tank system. We have basically our system model here, state model, with the holdup in the first and the second tank that changes over time. And you have basically your measure variables, which are actually the holdup in the first and the second tank. So naturally, this one is observable. That's clear. And what you see here basically are the control actions that are performed for basically the inflow here that you have out of your reservoir. And the thing that you see, initially you get a high inflow, then this goes down, and what you want is basically to reach this height in the first and the second. This is your objective. And you see how this overshoots a little bit and then decreases and reaches a set point, but it's a very smooth behavior. So this is actually very nicely operating controller. And as a model predictive controller, this should be the case. If this basically would be reached, so the startup is also something that cannot be done with a PID controller setup, because then you would basically have a huge differential here, and it would more or less get into oscillation. But if you have a small step point change here from 8 to 12 like that, and you want to go back to your set point, then you could tune your controller in such a way that it goes smoothly to that point. Then potentially like that, it would take a bit more time in order to reach that set point. On the other side, you could have it very aggressively tuned, that it goes up very high, and then it would realize at some point where it already passed that, okay, we have to go down. We'll go up, down, up, and you get such an oscillation. So such an oscillation is always a sign that it's tuned a bit too aggressive. As long as it is not maintaining the oscillation, it might be fine. On the other side, this could reduce basically the time until you reach your steady state, your set point. An example for a decentralized feedback control and central model predictive control here for our reactive dividing wall column we have in the laboratory. On the one hand, basically for both, now you're trying to control the temperature, not the composition in that case. You could do stabilizing control also with a central model predictive controller, just with the difference here that in order to keep the temperature in the pre-separator on the left-hand side here at a steady level, you would manipulate the liquid split, and for the side stream, you would basically manipulate the side stream flow rate in order to keep the temperature here constant, while for the temperature at that level, you would basically manipulate the steam or the energy input to the reboiler, and with the centralized model predictive controller, you would just take all the information on the temperatures and manipulate simultaneously the different manipulated variables, the liquid split, the distillate, and the side stream flow rate, as well as the energy input into the reboiler. And thereby, for a very nonlinear system as for the reactive dividing wall column, this has a big potential. And potentially for such a complex system, this is the way to go because the other one fails. But a little bit of spoiler, the left concept also works kind of well for stabilizing control if these disturbances are not too large. And that brings back to the part, if you have a set up control system, it depends on the task. So if it's stabilizing control, or if you really want to basically use the model predictive controller to obtain different set points, or for a batch process, you want basically an optimized recipe, in a sense, that if you have a very good model of that process, you might take a differential model for the process and take a model predictive controller to actually get your batch time down in the furthest possible sense by also avoiding some kind of side products or consecutive products, improving the selectivity of the reactor. You can have like an optimization running in parallel to the actual process, providing you with the actual control moves in order to get the time frame down for the batch and get optimized products. But for a steady state operational process, it might just be stabilizing against disturbances. And then such a simple structure might work well and is most of the time favored in comparison to something complex like that. And it might also be favored just because you don't exactly know what your system behaves like inside of the column.
Is there an example where they implement both? Is there an example where they can implement both?
For stabilizing control, you can always implement both. So the thing is, just you tend to use the simpler one. There are also some kind of heuristics, for instance, by Professor Leuben, who has a nice book on actual process control with a focus on distillation columns. Simple is always the way to go for, based on, in a sense, two reasons. It's simple to build up, and it's also simple to follow up by the operator. So if the operator knows that basically that controller acts on that manipulated variable in order to control that control variable, it's simple to understand. Looking back at that box, you just know there are a few measurements that go into the computer, and then the computer tells you, or tells the systems directly in the best case, how to manipulate those variables. So how to basically set the define the set point for the manipulated variables. And this is not easily grasped and cannot easily be followed. And you don't apply this if it is easy, usually. But what you can also do, and there's one example also in the course unit, not for the model produced controller, but for using a model-based controller, you not necessarily need to have the MPC directly telling you what to do or how to alter the manipulators. You may also use the MPC to basically specify the set point and then have the PID controllers work on adjusted set points. That might, for example, work well if you have a process where you want to go from one set point to another one. Okay, in yellow you just see again highlighted the parts which are the major benefits of a model predictive controller. Is of course more complex to build up, but it may offer you a solution in cases where the other one fits, or it may offer you additional advantages and benefits, for example, economic benefits for certain kind of applications where it just works significantly better than classical control structures. So as a last part, we have finished here with the process control part. You will have an exercise specifically related to the relative gain area in the next week. I just want to point out one last time, in our further courses at the Institute, we offer one course which in the next semester, which is on computer-aided process engineering, which is focused on basically the use of Aspen Plus as a process simulation tool, which is combined with a smaller part of the lecture on the methods of basically process safety and hazards, where we have a lot of lectures from industrial partners from Dow and Oli, just in the process of refining this, which will be clarified, I think, in the next 2-3 weeks with the colleagues from industry, that they also provide these lectures in English. We already switched the lecture of the parts of computer process engineering part to English, and this will be available for you as well. The only thing that you have to do in that case is then basically address this for the Prüfungsausschuss, that you want to introduce that module as an elective course this time, because we have changed this in the system, but it only gets valid for the next cohort. So for the students starting winter semester 2022. It is automatically in the catalog. For you, it is possible. You just have to basically write a short, proposition there for the Prüfungsausschuss that you would like to introduce this as an elective course. Let me know if you're interested, and I can talk with you about details. There. So as a last part from my side, we have introduced an evaluation sheet for the lecture and the exercises in StudIP, and it would be pretty happy if you could provide us with some feedback there. Any questions?
Could you give us some idea about what kind of questions will come in the exam?
I would say this question is very well referred to Mr. Fiedler in the next exercise. So you will have some, let's say, comprehensiveness questions here on the different topics, and there will be some tasks, 1 or 2. These tasks, of course, relate to the exercises. So the exercises, if you're basically well prepared for the exercises, you will be also well prepared for the tasks in the exam. And the other parts are basically questions which you should be able to answer based on the information that's provided within the lectures. So you don't necessarily need to think around the corner there, but you have to just grasp and comprehend the information that we provided there. Please address this once more with Mr. Fiedler. I tell him in advance that he can give you 1 or 2 examples there. Okay? Is that fine for you?
Oh, yes, thank you.
Okay, perfect. And if there are any other questions on regards of the exam, please also send them in written form to Mr. Fiedler and me together. Good, then I hope in face of the high current incidence numbers, you stay safe throughout the complete rest of the lecture period and the exam time, and I wish you good luck for the exam period. Stay safe.
Thank you.
Bye.
Thank you. Bye bye.